Hello everyone and a very warm welcome. In today's lecture, which is the 10th in the series Mathematical Methods for Economics, we're going to cover two topics that relate to graphs in particular. As I've mentioned before also, graphs are an integral part of this course that you are doing, and in today's lecture we will be covering two aspects relating to graphs, namely graph symmetry and the shifting of graphs. Graph symmetry is something I had touched upon briefly even in my previous lecture titled Quadratic Functions. So that is going to be the first part of the discussion. And in the second part, we're going to discuss the shifting of graphs, where we look at how the graphs of so many functions can be obtained through a reflection or a translation, basically some simple manipulations of some very basic functions. But let's get started with the discussion of graph symmetry first. So before I get into the formal details of symmetry, let me give you some intuitive sense of what we mean by symmetry, because that is going to be essential. It'll be good if you can get a visual idea of symmetry before we start. Now, there are various types of symmetries, but in order to understand things, let's think along the lines of symmetry about a line. For this, please take a look at this slide. The picture that I'm showing you here on this slide, here you have a parabola. Now suppose I draw a line through this parabola. This line is shown in red here. The question I can ask here is this parabola, is this graph symmetric about this red line? And the answer here would be yes, because you can think of the graph on one side of the red line as being a mirror image or a reflection of the graph on the other side of the red line. Alternatively, the way to think about things is that if you were to fold this graph along this red line, the two parts of the graph on each side of the red line, they would exactly coincide with each other. So that is the idea of symmetry. We will be talking about three types of symmetries in particular: symmetry about the x-axis, symmetry about the y-axis, and symmetry about the origin. And as a bonus discussion, I will also bring in symmetry about the line y equal to x. But let's first talk about symmetry about the x-axis. In this case, it is the x-axis that acts like a mirror, such that the portion of the graph, if you see the graph that I'm showing on this slide, the portion of the graph on top of the x-axis, above the x-axis, is a mirror image of the portion of the graph below the x-axis. These two portions can be seen as reflections of each other. Now here also, if I were to fold this graph along the x-axis, the two parts of the graph above and below the x-axis would exactly overlap with each other. Now what does this mean mathematically? This means that if I were to take a point like x comma y on the curve, then the reflection of this point x comma y, which is x comma minus y on the other side of the x-axis. So if we were to take the reflection of x comma y in the x-axis, that would be x comma minus y. Both these points should lie on the curve for symmetry about the x-axis. Now because both these points x comma y and x comma minus y lie on the curve, then that means that if I were to substitute these points into the equation of the curve, then both these points would satisfy the equation of the curve. And this then gives us the mathematical criterion for talking about symmetry about the x-axis. Basically, if I were to substitute minus y instead of y in the equation of the curve, that would leave the equation of the curve unchanged. So let me make things more precise. Basically, the graph that I'm showing you here is the graph of the equation x equal to y square. Now do this exercise in your mind. Suppose I substitute instead of y on the right hand side, I replace y by minus y. So what will that become? That will become minus y the whole square, which is nothing but y square. So here the equation we see remains unchanged. The equation of the curve remains unchanged if I were to replace y by minus y. And this is then the basis for defining symmetry about the x-axis, where we say that a curve is symmetric about the x-axis if and only if replacing y by minus y in its equation produces an equivalent equation. So the equation will remain unchanged if I replace y by minus y. Let's look at another example of symmetry about the x-axis. Here now you should be able to tell visually that this graph is symmetric about the x-axis. Just fold this graph along the x-axis in your do it mentally, and you'll see that the two parts of the graph above and below the x-axis will exactly overlap with each other. And let's look at how the math works. This graph is the graph defined by the equation x equal to mod y. Now let's replace y by minus y, and that is going to give us on the right hand side mod of minus y, which in turn is equal to the absolute value of minus 1 times the absolute value of y, because we know the property of absolute value that if we have the absolute value of the product of two numbers, that is nothing but the product of the absolute value of the two numbers. And here our two numbers are minus 1 and y. So the mod of minus y is going to be mod minus 1 times mod y, and we know mod minus 1 is 1 itself. So this is going to give us mod y, and here we go. We see that the equation is still x equal to mod y when we replace y by minus y. So the equation remains unchanged, and here also we have symmetry about the x-axis. Let's look at yet another example of symmetry about the x-axis before I move on to a discussion of symmetry about the y-axis. Here I'm showing you the graph of xy square equal to 1, and here again we have symmetry about the x-axis. At this point in the course, we don't expect you to be drawing all these graphs. If you can draw them, well and good, but you will be able to draw all these graphs once we do calculus, differentiation in particular. Just for your information, I draw all these graphs using the software Mathematica, and that's an excellent software. So if you ever get a chance to do a course on Mathematica, please go ahead and do it. Now, this is as far as symmetry about the x-axis is concerned, and before I move on to the y-axis symmetry, just note that all the graphs that I've shown you so far for symmetry about the x-axis, none of these graphs were graphs of functions, because all these graphs for symmetry about the x-axis that I've shown would fail the vertical line test. Now let's look at symmetry about the y-axis. In this case, it is the y-axis that acts like a mirror, such that the portion of the graph on the right side of the y-axis is a mirror image or a reflection of the portion of the graph on the left side of the y-axis. Mathematically, this means that if I were to take a point like x comma y on the curve, please look at the curve on the slide. If I take a point like x comma y, then the reflection of this point on the other side of the y-axis, which is minus x comma y, will also lie on the curve. So basically, if I were to replace x by minus x, that will not change the value of y that I get. The height of the graph remains the same for both x and minus x. Now, because both x comma y and minus x comma y lie on the curve, both these points must satisfy the equation of the curve, which is to say that if I were to replace x by minus x in the curve, in the equation of the curve, the equation would remain unchanged. And you can see here how it works mathematically. The graph that I've shown here is the graph of the equation y equal to x square. So if you see where my cursor is pointing, now if I replace x by minus x on the right hand side of the equation, y equal to x square, then I'm still going to get x square, because minus x squared is x square, and that we see leaves the equation of the graph unchanged. So we say that a curve is symmetric about the y-axis if and only if replacing x by minus x in its equation leaves the equation unchanged. And that is the criterion we're going to use. This is another example of a function here which is symmetric about the y-axis, and but again, please note here that you may also have a curve which is symmetric about the y-axis, but it need not represent a function. So for example, if you look at this graph, this is a graph that is symmetric about the y-axis. Actually, it's also symmetric about the x-axis if you see things through. And this is clearly a curve that it's a graph that will fail the vertical line test. It does not, this graph does not represent a function. However, if we were to talk about functions, the question here is, can we come up with a mathematical criterion for a function that is symmetric about the y-axis? Now let's take a look at this graph again, which is representing a function. We said here that for symmetry about the y-axis, both the points x comma y and minus x comma y being the reflection on the other side of the y-axis, both these points will lie on the curve. So this is to say that if I were to evaluate the function at minus x rather than x, the value of the function would remain the same. Therefore, we can say that for a function that is symmetric about the y-axis, it must be the case that f of minus x is equal to f of x, for all values of x in the domain. And such a function which is symmetric about the y-axis is also known as an even function. Let's look at some other examples of even functions, basically functions which are symmetric about the y-axis. So here, if you take a look at this function, f of x equal to x square plus 2 times x to the power 4. Here, if you see, this is an even function, because if I were to if I were to calculate f of minus x, that would give me minus x squared, which is x square itself, plus 2 times minus x to the power 4, which is again x to the power 4. So the equation remains unchanged if we replace x by minus x, and therefore we see that f of minus x is equal to f of x. Similarly, you can try this as an exercise on your own. If you take the function g of x equal to mod x, this is also an example of an even function. Now, note here that just because you have an even exponent in the equation, it does not, or even exponents for that matter, that does not necessarily mean that you have an even function. So, for example, if we take a function like f of x and define it as f of x equal to x plus 2 the whole square. Please take a look at this slide. Here, if f of x is equal to x plus 2 the whole square, then f of minus x is going to be minus x plus 2 the whole square, which is basically 2 minus x the whole square, and that we see is a different mathematical expression. Clearly, f of minus x is not equal to f of x here. And to see things even more precisely, let's take some numbers. So, for example, if x is equal to 2, then f of x is equal to f of 2, which is 2 plus 2 squared, which is 16. But f of minus 2, which is f of minus x, f of minus 2 is going to be minus 2 plus 2, which is 0. So, 0 squared is 0. And clearly, we see here that f of minus x is not the same as f of x. So, just because you have an even exponent, just don't jump to the conclusion that that will make for an even function. Right. So, till now we have talked about symmetry about the x-axis, and in the second part we talked about symmetry about the y-axis. As far as symmetry about the y-axis is concerned, this can also be viewed alternatively as symmetry about the line x equal to 0, because if you take any point on the y-axis, all the points on the y-axis would have the x coordinate as 0. Now, in general, we can also talk about symmetry about the line x equal to some number p. So we say that a graph of a function is symmetric about the line x equal to p if f of p minus t is equal to f of p plus t. So if you were to take the value of the function t units to the left of this axis of symmetry, the line of symmetry, that value would be the same as the value that you get t units to the right of the line of symmetry. So let's look at an example here. Suppose I give you this function defined by the equation y equal to 2x square plus 3x minus 1, and I ask you to find the line of symmetry, which is to say that I have to find the value of p in the expression f of p minus t equal to f of p plus t. So let's go ahead and do that. F of p minus t here is 2 times p minus t the whole square. Just instead of x, put p minus t. So you'll get 2 times p minus t the whole square plus 3 times p minus t minus 1. And on the right hand side, we'll have f of p plus t, which is 2 times p plus t the whole square plus 3 times p plus t minus 1. Now, if you just simplify the expressions here, you will get minus 4 times pt minus 3t is equal to 4 times pt plus 3t. And here you can see the t's will get cancelled on both sides, and this then implies that 8p is equal to minus 6, which in turn implies that p is equal to minus 3 by 4. So here your line of symmetry will be defined by x equal to minus 3 by 4. And in fact, this should look familiar to you if you have heard the lecture on quadratic functions. The example that I've given you, the equation that I've given you here is actually it's a quadratic function. And if you remember what we did in the previous lecture, we said, I proved this result for you, that the parabola defined by the function f of x equal to ax square plus bx plus c, that is symmetric about the line x equal to minus b upon 2a. Now for this quadratic function, our b is equal to 3 and a is equal to 2. So minus b upon 2a would be minus 3 upon 4, and that is exactly what we have got in our calculation above. So in this way, using the formula f of p minus t equal to f of p plus t, we can calculate symmetry about the line x equal to p in general. Okay, let's now look at symmetry about the origin. Symmetry about the origin means that if the point x comma y lies on the curve, please take a look at this graph. If the point x comma y lies on the curve, then its reflection through the origin, which is minus x comma minus y, that will also lie on the curve. Which is to say that if I were to replace both x and y by minus x and minus y respectively in the equation of the curve, the equation would remain unchanged. So for example, the graph here is the graph of the equation y equal to x cube. So let's replace x by minus x. You'll get on the right hand side minus x cube. And on the left, if I replace y by minus y, I'll get minus y. The minus signs on both sides will get cancelled, and you'll still be left with the same equation, y equal to x cube. So therefore, we say that a curve is symmetric about the origin if and only if replacing both x by minus x and y by minus y in its equation leaves its equation unchanged. Let's look at another criterion which we can use for symmetry about the origin, and this is an interpretation which is in terms of a 180-degree rotation of the graph. So what you could do is, for the graph that I'm showing on this slide, you could take a picture of this slide on your camera and just rotate it. You have this rotate feature in your camera. Just rotate this graph 180 degrees such that you get a picture like this. Basically, the part of the axis where you have the label x, that will now appear on the left. So once you rotate the graph 180 degrees, you'll see that you actually get the same graph. So when we talk about symmetry about the origin, that means that the graph is invariant to a rotation of the curve by 180 degrees. And you can also think through things in this fashion. A 180 degree rotation basically means that you first reflect the graph in the y-axis and then reflect it in the x-axis. So there'll be two reflections happening here, and in the end, the result that you'll get will be the same graph. This is another example here on this slide of a graph that is, in fact, this is a function which is symmetric about the origin. This is the graph of sine x, and here you can see that if I were to replace x by minus x on the right hand side, you would get sine of minus x, which is nothing but minus of sine x, and on the left you would have minus y. Once I replace y by minus y, and again the minus signs would get cancelled, and you'll be left with the original equation. Okay, so now let me show you another example of a graph that is symmetric about the origin, and this is our well-known circle. So this here is a graph which is symmetric about the origin, and here we don't have a function, but nevertheless this is a curve that is symmetric about the origin. But if you notice here, a circle will have rotational symmetry about the center for any angle, because you could rotate it by any angle, not just 180 degrees. You could rotate it by any angle. The graph would still remain the same. In fact, a circle would also have reflection symmetry about any line that passes through the center of the circle. So just draw any line through the center of the circle, any line, and you'll see that the circle is going to be symmetric about this line. So a circle has reflection symmetry about any line that passes through the center, and it also has rotational symmetry for any angle, and this is rotational symmetry about the center. Okay, so let's now focus our discussion on functions in particular. So let us ask ourselves, if we have a function which is symmetric about the origin, then what would be the mathematical criterion that we can develop for defining such a function? Now, as I mentioned before, when we talk of symmetry about the origin, it means that both the points x comma y and minus x comma minus y will lie on the curve, which is to say that if I were to replace x by minus x, I would also have to replace y by minus y, and for a function minus y would be nothing but minus f of x. So the mathematical definition of a function which is symmetric about the origin will be that f of minus x will be equal to minus f of x for all x in the function. And such a function which is symmetric about the origin is also known as an odd function. Examples of odd functions would include functions like functions defined by y equal to x cubed minus x. Here you can see that if you were to replace both x and y by minus x and minus y, respectively, the equation would remain unchanged. And similarly, y equal to x, this equation would also give you a function which is symmetric about the origin. Right. Again, remember that just because you have an odd power in the equation, that does not necessarily make for an odd function. So for example, if I give you an equation y equal to x cubed plus 1, note here that this is not an odd function, and you can check it in this way. If you calculate f of minus x, so our equation here is y equal to x cubed plus 1. F of minus x here would be minus x cubed plus 1. And minus f of x is going to be minus x cubed minus 1. So clearly f of minus x is not equal to f of x. Right. As an additional bonus discussion, let us talk about symmetry about the line y equal to x. This is a line which is passing through the origin and making an angle of 45 degrees with the x-axis. So here you can see visually that this is going to be an equation which will remain unchanged. if both the x and y coordinates are interchanged. So for example, the graph that I've shown you here is basically a graph carved out of the equation x cube plus y cube equal to 6 times xy. This is also known as a folium of Descartes, and here you can see that if I were to interchange y and x in the equation, I would get y cube plus x cube is equal to 6 times y times x, because instead of x I'm putting a y, and instead of y I'm putting an x, but the point is that's still going to give us the same equation as the one that we have here on this slide. So that is symmetry about the line y equal to x, where the equation remains unchanged if the x and y coordinates are interchanged. This is another example where the curve is symmetric about the line y equal to x. This is defined by x cube plus y cube equal to 1, and again y equal to minus x is another example which I'm showing you here to show symmetry about the line y equal to x. So let me see if you've understood the idea of symmetry. So let's run through this example where I've given you this equation x times y minus 5 times x square is equal to 4. So let's test this equation for symmetry about the x-axis, symmetry about the y-axis, and symmetry about the origin. So if you remember, we said a curve is symmetric about the x-axis if the equation of the curve remains unchanged if you were to replace y by minus y. So now if I replace in this equation, if I replace y by minus y, I'm going to get x times minus y minus 5x square is equal to 4, and clearly that would mean that I'm going to get minus x times y minus 5x square is equal to 4, and this is clearly not the same as the original equation that we started out with. So this equation is not going to be it's not going to give you a graph that is symmetric about the x-axis. Okay, for symmetry with respect to the y-axis, we will replace x by minus x now. So if we do that, we're going to get minus x times y minus 5 times minus x the whole square is equal to 4. And this in turn implies that minus x times y minus 5 times x square is equal to 4. And again here we are left with an equation which is not the same as the original equation. So here again we will not have symmetry about the y-axis. Finally, let's test for symmetry about the origin, and here you can see that if I replace both x and y by minus x and minus y respectively, I'm going to get the same equation. So let's do it. If I replace x by minus x, I'm going to get minus x times minus y because I've replaced y by minus y. Minus 5 times minus x squared is equal to 4, and this then implies, because minus x times minus y will become x times y, xy minus 5x squared is equal to 4, and here we have an equation which is identical to the original one. So yes, we do have symmetry about the origin. And since we were discussing symmetry about the line y equal to x, that is also something that you could check out for here. So just interchange the x and the y coordinates, and here you'll see you'll get y times x minus 5y squared is equal to 4, because x becomes y and y becomes x. So clearly this will not give us symmetry about the line y equal to x. So here in this example for the equation that we have, we only have symmetry about the origin. Okay, so that finishes the first part of our discussion. In the second part of our discussion, we're going to talk about shifting of graphs through what are known as translations and reflections. In particular, there are 4 kinds of translations that I will be talking about, and 2 types of reflections as well. So the question here that we're going to address is as follows. The question, I can express this question like, if I start with the graph of y equal to f of x, then what are the other graphs that I can obtain from this particular graph? There are 4 translations that we will be talking about. Please take a look at this slide. So in particular, we will talk about how we can obtain the graph of f of x plus c, f of x minus c, the graph of f of x plus c, and the graph of f of x minus c from the original graph, which is given by the equation y equal to f of x. And here please note that c is a positive constant. So let's start talking about these translations. The first operation that I'm showing you here is one that involves adding a positive constant c to the function f of x. So our new equation becomes y equal to f of x plus c. The way to read this equation is that if I were to look at the same value of x as the value of x in the original graph, what will be the value of y as defined by this new equation? The value of y for a given value of x would now be c times more than the value that I had in the original function. And this in turn has the geometric effect of shifting the graph, the original graph, up by c units. So this is nothing but a vertical upward shift, or you could think of it as the graph being translated c units upwards along the y-axis. So here I've given you this example where I've started with the graph of y equal to x square, and let me just tell you that for all the graphs, the shifting that I will be showing you on all these slides, the original graph is what I've shown you in pink, and the final graph is what I'm showing you in blue. So here I'm starting with the graph of y equal to x square, and you can see here that the graph of y equal to x square plus 2 is nothing but a vertical upward shift of the graph y equal to x square by 2 units. The second operation is one, the second operation on y equal to f of x is one where I subtract c units from the original function f of x. And this in turn gives us the equation y equal to f of x minus c. That is a new equation. And the geometric effect of subtracting a constant c from f of x is that the graph is going to shift down by c units, or it gets translated by c units along the y-axis. So here again, if we start with the graph of y equal to x square, then suppose if I want the graph of y equal to x square minus 2, that will be nothing but a downward shift of the graph y equal to x square by 2 units. Okay, now this is the interesting shift that I would like you to focus on. Here the question is, how can we obtain the graph of y equal to f of x minus c from the graph of y equal to f of x? So here the geometric effect that I'm going to show you is that when I want the graph of f of x minus c, that is nothing but a rightward shift of the original graph f of x by c units. So for example, if I have y equal to x square, and I want to obtain the graph of y equal to x minus 2 the whole square, the graph of y equal to x minus 2 the whole square is nothing but the original graph of x square shifted 2 units to the right. Now the question that many students have at this point is, why does having f of x minus c shift the graph c units to the right and not c units to the left? So let's try and understand this. And to make you understand this, I will use the same example that I had used on the previous slide. Let us again look at the graphs of x square and x minus 2 the whole square. And for both the graphs, let's just fix a particular value of y. So let's suppose, please take a look at this table here. So let's suppose I fix the value of y at 0. Now let's ask ourselves a question. For the first graph, what is the value of x? That will give us y equal to 0. Now the first graph is our original one where y is equal to x square. So what is the value of x that will give you y equal to 0? That is nothing but x equal to 0. Now let's ask this question again for the new graph. So our new graph is y equal to x minus 2 the whole square. And what is the value of x that will give you a value y equal to 0 for this new graph? That is going to be x equal to 2, because 2 minus 2 the whole square is 0. So that is 1. Now let's take another value of y. So I'm just doing a couple of exercises and we'll see a pattern emerge. So now suppose I take y equal to 1. Now what is the value of x that will give us a value y equal to 1 for the original graph? That will be either plus 1 or minus 1. So let's for the time being focus on minus 1, the lower value of x. And again we can ask the question, what is the value of x that will give you a value y equal to 1 for the graph y equal to x minus 2 the whole square? And here you can see that x can be either 1 or 3, because if you substitute x equal to 1 in the new graph, you're going to get 1 minus 2 the whole square, or if you substitute 3, again you're going to get y equal to 1. So let's take the lower value again. So here the value of x that will give you a value y equal to 1 is going to be x equal to 1. And similarly, we have the points where x is equal to 1 for the original graph and x is equal to 3. And if you take a look at the numbers that we have on this table, all the values for the new graph, all the values of x for the new graph here where my cursor is pointing, those are all 2 more than the values of x for the original graph. And that is nothing but to say that if I keep the value of y the same, if I fix the value of y for a given value of y, the new graph x minus 2 the whole square will lie 2 units to the right of the original graph y equal to x square. So I hope things are clear here, and you can listen to this recording again if you would want to, if you still feel you need to understand things. So, but you should be clear that whenever you have x minus c, f of x minus c, that is to imply that there's going to be a rightward shift of the original graph. And similarly, if I want to obtain the graph of f of x plus c from the graph of y equal to f of x, then that is going to have the geometric effect of shifting the graph c units to the left, or in other words, the graph gets translated c by c units along the x axis to the left. And for example, if I want the graph of x plus 2 the whole square, that is going to be nothing but a leftward shift by 2 units of the graph y equal to x square. So these are the 4 operations for translations that I wanted to talk about. Let's now talk a little bit about reflections, and there are 2 kinds of reflections that I will be talking about. First, we'll talk about how we can obtain the graph of y equal to f of minus x from the graph of y equal to f of x, and we'll also talk about how we can obtain the graph of y equal to minus f of x from the graph of y equal to f of x. Okay, so let's take a look at the first kind of reflection, which I'm calling operation 5 on y equal to f of x. Here our new equation is y equal to f of minus x. That is the graph that we want. Now let's just get a sense of things. Let's just read the math. The way to understand this equation is that now if I were to replace x by minus x in the function, I want to get the same value of y. So the height will remain the same, but now instead of x, I'm going to have minus x, which is to say that the original graph will get reflected in the y-axis, because once it gets reflected in the y-axis, the y-coordinate will remain the same, but instead of x, you will have minus x. And as an example, I've shown you here the graph of y equal to square root of x, which is a graph on the right-hand side of the y-axis. It's labeled here. That is the graph in pink. And the reflection of this on the other side of the y-axis is nothing but the graph of y equal to the square root of minus x. And you can see here that for any given value of y, the x coordinate for the original graph, if that is x, then the x coordinate would be minus x for the new graph y equal to square root of minus x. And finally, let's talk about how we can obtain the graph of minus f of x from f of x. That in turn is nothing but a reflection of the graph about the x-axis, because the way to read the math in the new equation is that now if you keep the x value the same, the y value in the new equation would be negative of the y value that you had in the original function. So for example, if we start with the graph of y equal to square root of x again, then the graph of minus square root of x would just be a reflection of the original graph in the x-axis. So that is as far as the discussion of translations and reflections goes. Let me quickly walk you through a couple of examples to illustrate the shifting of graphs. So for example, if I ask you the question, draw the graph of y equal to 1 minus x plus 2 the whole square, and you do that from the graph of x square, y equal to x square. So the slide here shows you the graph of y equal to x square. Now let's from here obtain the graph of x plus 2 the whole square. The graph of y equal to x plus 2 the whole square would just be a leftward shift of the original graph y equal to x square by 2 units, and then we will reflect it in the x-axis to get the graph of y equal to minus x plus 2 the whole square. And finally, now we just have to add 1 unit to each point in the graph to get y equal to 1 minus x plus 2 the whole square, and this final graph is the graph in blue here. So this is how we can show the shifting of graphs stepwise, and we can get our final graph from just a very simple graph, which is y equal to x square. Let's look at another example. Suppose I ask you to draw the graph of y equal to mod x minus 1 plus 3 from the graph of y equal to mod x. So here I've shown you the graph of mod x, y equal to mod x. To get the graph of mod x minus 1, I will shift the graph of mod x 1 unit to the right, and then I'm going to add 3 units to the graph of mod of x minus 1 to get our final graph, which is shown here in blue, which is the graph of y equal to mod x minus 1 plus 3. And just one more example before we end this lecture on symmetry, translations and reflections. So here you have to draw the graph of y equal to square root of x plus 3 minus 4. And here you start with the graph of square root of x. So this graph here in pink is the graph of the equation y equal to square root of x. The graph of square root of x plus 3 would imply a leftward shift of the graph of square root of x by 3 units, and that is shown here as a leftward shift. And then you just shift the entire graph of square root of x plus 3 down by 4 units because you're subtracting a 4. So this then here, this curve is the graph of the equation y equal to square root of x plus 3 minus 4. So I guess we'll have to end it at that. That's all we have time for today in today's lecture. In the next lecture, I'm going to bring in some economic applications of quadratic functions and also the circle. I talked about these concepts in theory, but let's now bring in some economic applications. So see you soon again. Bye-bye.